Welcome Mechanics of Materials students. In this lecture we're going to discuss torsion of circular shafts. So this is very likely one of the first applications of all of the concepts of Hooke's law, stress strain, and stress and strain at angles to designated axes that you're going to encounter in your study of mechanics of materials. It's a very simple application because, as you'll find out, there's a lot of directions in our reference coordinates that actually don't have any strain. And that makes it very simple to relate displacement, angular displacement, applied moment, and our stress and strain through Hooke's law. So we're going to step through this. So we're going to start with a cylinder where the axis is oriented along the z-axis of our coordinate system. We have the r axis designating the radius of the cylinder or in the radial direction, and then our theta direction is circumferential around the edge of the circle. So rather than an xyz, we obviously have cylindrical coordinates, so we have an r theta z. And of course we can apply everything we've done with Hooke's law to r theta z just like we did to xyz. We can apply our shear modulus, and we can apply all of Hooke's law. So first and foremost, we're going to go through the assumptions for elastic torsion. This is twisting of a shaft. And these are very, very important for deriving the relationships that we're going to use. And we need to remember that anytime we're applying these in a real-world situation, we need to make sure that the actual deformation is small so that these assumptions apply. Because if they don't, then the basis of our derivation isn't there anymore. But we're going to assume that we've got small deflections, so small twists, which is pretty common in regular use. So assumption number one, no deformation in the r theta plane. So this circular face and every slice we could imagine taking in the cylinder, anything on that slice stays the same in shape and size. So the cylinder's not getting fatter, it's not turning into an ellipse cross section, it's not doing anything funky. So no deformation. So that means no normal stress in the r, no normal stress in the theta, and no shear stress in the r theta. No deformation in the r theta. Furthermore, we don't have any assumption number two. There's no change in the axial direction. So our displacement in the z, the axial direction of the cylinder, is zero. So no E normal strain ZZ is also going to be zero. It doesn't get any longer or shorter. So the only deformation we have is rotation of these kind of, we can call them like pepperoni slices in the r theta plane about the z-axis. And one example, kind of a visualization, is if you take a stack of coins and you stack them up in front of you and you paint a stripe down the stack, and then you twist the coins such that the line that you've drawn becomes kind of a slanted line. That's the exact motion that we're modeling. So just twisting of non-deforming slices. The pepperoni slices don't ripple, they don't turn into ellipses, they just spin on their axis relative to each other. So basically all of the motion is in the theta z direction. So let's grab some reference points on a hypothetical cylinder and see if we can't put some quantitative description to this twisting. All right, so now we've got like a little reference cylinder. So now we're looking at small dimensions. So rather than some finite z of like a foot or a centimeter, it's dz. So it's a small slice. And we've got a twist angle. We're going to twist this little element, and so we're going to twist it an angle of d phi here. And we've got the center of the little cylindrical element noted as O, so like our origin. And we're going to look at a couple of points out on the circumference. We're going to look at point A that moves over to point A prime due to this twist. And down here at the bottom of our DZ element we have point B, which doesn't move anywhere because we're not rotating the cylinder. If we rotated the cylinder, we'd have B going from B to B prime, but the cylinder's twisting. So we're actually inducing a shear strain in the theta z direction, and so B stays still and A moves. So we have displacement of A to A prime through the angle d theta. B stays the same, so we end up creating this angle gamma in the theta z direction. So if we start assigning strains, both normal and shear, to these displacements that we've created based on points moving from one position to the other, we can start kind of populating our strain matrix. So we're going to start, I'm going to just walk right down through it here. So we got point A, it goes from A to A prime, and the radial distance stays the same though. So OA distance and OA prime are the same. Therefore, because our coin didn't change shape, that was, we twisted it on its stack. So normal strain in the R is 0. We can define our angle OAB, so from the center to A to B, if you look at that, that's 90 degrees. And if you look at O to A to B, believe it or not, that's also 90 degrees, because you're just literally tracing down the side of the cylinder. Now the plane is tilted, but that actual angle is the same. So if you look at it, one is a vertical slice through the cylinder, the other is a slanted slice, but the angle OA prime B and OAB, they're both 90 degrees. Because of that, we can say that the shear strain in the RZ direction is 0. So we've knocked 2 out. We had earlier prefaced that there's no R theta deformation, so anything on that slice, that cross-sectional slice, is unchanged in size or shape. So that means our normal stress in the theta direction has to be 0, and our normal strain in the theta direction has to be 0, and our shear strain in the R theta is also 0. And of course we've now have a double reason why our R strain, normal strain in the R direction, has to be 0. So we've kind of given 2 reasons for that. So there's not a lot left in our strain tensor here. The only thing that we haven't designated is 0 really is shear strain in the z theta, because we had earlier, we're not writing this down here, but earlier we had said there's no change in the axial direction, so that means that our normal strain in the z is also 0. So we only have one component of the entire strain matrix that isn't 0. This is an incredibly simple situation from the point of view of doing our calculations. And furthermore, we've got a great way of designating what it is. So we can say, well, shear strain in the z theta is the same as theta z. So we can basically look at the tangent of this angle phi, or excuse me, gamma. This is phi up here. We're looking at gamma for z theta. So we can say the the opposite side is AA prime, and the adjacent side is AB, and our hypotenuse over here is B to A prime. So for a small angle, we can say the tangent of the angle and the angle is about the same if we take the angle in radians. So we can say our strain in the theta z is simply going to be AA prime over AB. Okay, well AB is dz, and A to A prime is our circumferential arc length, which is defined by r d phi. I got a d phi, but r is just our difference between point O and point A. So we've got AO d phi, which is r, so we can say we've got now a fairly simple expression for the one and only strain associated with circular shaft or any kind of shaft, torsional deflection. Okay, and the d phi dz is known as the angle of twist or rotation. For those of you who may work with fasteners, and look at threading engagement for fasteners. The quote-unquote angle of twist is something you might hear about, and so that's the same kind of motion. In that case, it might be advancement of a fastener rigidly, but in this case, we're looking at the twist as the twist angle of rotation. And here's a little reminder: only applies for very, very small gamma. And this requirement for small, and we mean small angle approximation, like, a couple of degrees max, maybe less than 5. We're making a small angle assumption when we equate the tangent to the actual angle to get our shear strain in the theta z. We're making a small angle assumption when we say there's no deformation in the r theta plane, because if we twist it enough, we might start buckling. Same thing with the z direction. So almost every assumption we've made that have given us this great simple expression has been predicated on this will only be true for small angles. So if somebody's telling you they've got some kind of rubber or an elastomer and they're twisting it to like 45 degrees, this isn't going to apply. But maybe a steel shaft that's being used to drive a propeller, or some kind of, or a beam that's twisting a little bit due to an applied moment about its axis, this would definitely apply in most of those cases. Okay, so we have a strain, and we have an expression for that strain in terms of the first derivative of a twist angle per unit length along our shaft and the radius of the shaft. Strains are great to measure. If you've gone through your sections on strain measurement, you'll know that we can probably measure this gamma z theta with a strain gauge, a couple of strain rosettes. But if we wanted to relate this to maybe a predicted twist angle for a given dimension of cylinder, of shaft that we're going to twist, we kind of need to go, instead of thinking in terms of strain, we might want to think in terms of stress that maybe we could relate to an applied moment, because that's something we designated. When we could say don't twist it any more than this, or we're going to get too big of an angle of twist, and maybe that doesn't work for our structure. It would be a deflection limited design in that case. So let's use Hooke's law, and instead of expressing strain in the z theta, let's use our relationship between shear strain and shear modulus here to relate our angle of twist and radius to a shear stress. So we can say our shear stress in the z theta direction is going to be equal to our shear modulus times the radius times our angle of twist angle of rotation. Okay, so now we have shear stress, modulus, radius, twist angle per unit length on the shaft. So twist angle is our deflection, something we might want to limit, or we might need to achieve if we're designing something where we want something to twist in a predictable way. We could presumably measure the radius of our shaft, look up our modulus, but shear stress, well, it is definitely related to forces and moments. It's not like something you can designate with a torque wrench or with the force applied at a unit distance on some kind of machine or with a load. So now we have to go from shear stress to moment. And so we're just going to add up shear stress across the entire area of the shaft face and relate that to moment. So we've got our shaft, our cylinder drawn again, and we've got a little annulus, a little donut ring, where its outer radius is at r, and it's thin. It has like a dr radius to it, this little donut in the middle. And we can imagine shear stress in the z theta kind of acting along this, on the face of this little donut. A thin annulus of area dA. So it's going to be 2 pi in the theta direction times dr will give us our integrated around 2 pi r dr to give us our annular ring area. And as r changes, the resultant moment due to the cumulative force from adding up all of that shear stress is going to give us our mz, our applied moment. So what we're doing is now we're basically saying, okay, I have an expression for shear stress. I can add up the shear stress across an area to get a shear force, equivalent force, and then I can remember that that force is acting at a particular r, specific to r, which will then give me moment. So I've merely added up what's effectively a distributed load. So that's what we're doing with this. And of course we're going to make the assumption that all of these little annular radii, or the annuli at all of the different radiuses have the same shear stress. So we have a uniform z theta shear stress across the whole face. So it's constant. We can take it out of the integral. So we're going to start with force on our little annulus. So that's just going to be our shear stress, same everywhere, times r dA. And this is actually the force part of it is tau dA, and we turn that into a moment by multiplying by the radius at which that area happens to be sitting. So this is the moment. I shouldn't say force, I should just say moment, because in this case we're worried about moment, not force. We're not sliding something, we're twisting it. So r tau dA is the moment if we add it up over the whole dA. So all we have to do is integrate to get the actual moment that results in that shear stress, which results in that angular deflection per unit length on the shaft. So here's my tau. I can drop in the whole expression for tau. I've got an r. Oh, it had an r come in with my expression for tau. I'm going to integrate over the whole area. So if I rearrange that and I assume that we're not going to have any changes in the twist angle as I go along the shaft. We're isotropic, we're homogeneous, our shear modulus doesn't change with length along the shaft, our radius isn't changing with length along the shaft. So I can take, in that case, if all those are true, I can take my d phi dz out of the integral, I can take my shear modulus out of the integral, and what am I left with in the integral? R squared dA, which, if you remember moments of inertia maybe from dynamics, this is the polar moment of inertia for a circular cross-section, neglecting mass, so it's kind of the polar centroid, center of inertia divided by the density. So we're not including mass, but everything else is the same, that we have an r squared being added up over the entire area. So this is the cumulative squared distance of every bit of area from this central axis. So why do we care? Because that's something convenient to look up. That's IZZ, actually, something that we're going to see a lot more of when we look at beams. So this is a good introduction to how the moment of inertia for a given shape of cross-section has a lot to do with how that material responds and deflects for a given loading. So our applied moment that we're going to grab the shaft and twist is equal to shear modulus times our twist angle per unit length times this polar moment of inertia, which we can just express as IZZ. So here's our expression. We can designate what we apply. We can look up G in a handbook. We can look up IZZ for a given cross-sectional area. And here's the twist angle per unit length. So for every so many inches you go down the shaft, you're going to get so much twist, and you can add it up. So this has to be very small, but of course if you have a shaft that's maybe a mile long, you might accumulate a lot of twist without violating your small angle assumption. Not that I'm recommending you make something that'll be a candy cane. So if we restrict ourselves to circular shapes, we can kind of, we can make some, not assumptions, but we can designate what our IZZ is going to be and express it in terms of the radius of our shaft. So that's big R. So we have a IZZ is pi r to the 4th over 2, and we can drop that in if we want. And then that would allow us to just, all we would need to have is the radius, our modulus, how hard are you twisting, and we'll get basically our twist angle of deflection. Or if somebody went and measured the twist angle of deflection and said, hey, I need something to deflect. Maybe I'm making something that's going to have a dial indicator at the end and I need it to rotate. We could be given a twist angle of deflection or a total deflection at a given distance that we need in radians, and a shaft diameter and a modulus, a material somebody wants to use. How much torque do I have to apply to get that deflection for a shaft this long? We can just integrate this expression. So basically you can get any one if you know the other three variables. So we're going to summarize the relationships here we have, and these all just fell out of our assumptions of really strain in one element of the strain tensor only, that gamma theta z being all we had. So all of this dropped out. We have applied moment being equal to shear modulus, moment of inertia for the cross section, times the rate of twist angle per unit shaft length. We can isolate our twist angle per shaft length in terms of three other things that in general will stay constant along the shaft or might vary in a way that we have a relationship with z. Maybe we have an angle that or a radius that changes as we go along the shaft. Well, in that case, IZZ would just be a function of z. Well, we could integrate that with respect to z if we had a continuous function, or if it went in steps, we could do partial integrals over each section of the shaft based on its radius. So either way would work. We can, basically integral of the sum is the sum of the integrals. We could even, if we needed to, deal with something that maybe had a different modulus in different sections. So as long as we had it as a function of z. And then, of course, we can go back and relate to shear stress in terms of the others, just rearranging again and writing basically our d phi dz in terms of our strain and go back to stress. This might be useful if we're worried about somebody applying too much stress. So we might look at our yield strength of a material and then go through our Mohr circle stress transformations and say, okay, what is the max shear stress associated with my known tensile strength, my capabilities? And then that would be the max number that you would allow somebody to apply. So if somebody needs to get a certain angular deflection from some material for some reason in a circular shaft, you could say, okay, you can apply moment and for this given configuration up to the shear stress that corresponds to yield minus some safety factor that you'd want to apply. So these three relationships all allow you to design or check for different things that might be important in your design or for your material. Okay, we're gonna stop here, and then we're gonna come back and pick up with a quick application of how to use these three together, and then we'll turn our attention to strain energy and a couple of additional examples.